Hello everyone, I'm going to introduce one of the cluster analysis ways that we can use called kmeans to group different objects in one group so that they share the more similarities than others. So kmeans, as we know, we can download and use a library from online using Python library, and there are few files I want to introduce here. So there are four main files, the Python files: kmeans class, cloud, and predictcloud.py files, and one more Jupyter notebook files that we can run on the notebook to show the result for us to see it easily, and two more Excel files. One is this test4 Excel file. This is the data file, original data file we want to analyze. The other one is a parameter file. So data file has all of the element contents in percent. So for example, silicon in this object has 19%, while the aluminum has much less. And all of the data file we want to analyze so that we can group, for example, this one and to which group 1, 2, 3, 4, whatever. So we have many objects to analyze. And the other file, Excel file, is a parameter file. It has the parameters of this model, kmeans model. For example, clusters 3, 4, 5. We can choose 3 or 4 or 5 groups that we want to group. And the initialization ways, we have kmeans++ or random that we can choose. I will explain later more about this. And okay, this is for kmeans, and also we can adjust it a little bit more so that we can get weighted kmeans, wkmeans in short. So wkmeans also has three main files and one test class, the Jupyter notebook file, and the main data file, as well as a feature Excel file. So this feature Excel file, I put it here as an input directly here, means I want to iterate this code for 10 times, or this loop, and also the cluster groups number of clusters I want to group is 4. And there are two more ways. One is called AFW kmeans, and the other one is called kmeans input weight. Kmeans input weight is what it is so called. We can input weight from our side. For example, the weight is over here, because there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 parameters, and we can give them different weights. For example, we can just set everything very easy so that they have the same weight from silicon to oxygen. That's called input weight. That means we can input weight from outside. Another way to group called AFW kmeans. What does AFW means? So there's one paper of this kmeans cluster analysis with AFW means adaptive feature weighting. So I use this paper to group in this way. And there are also 3 main Python files that we can run: AFW kmeans, class, and cloud. And also all of them can create the result, saving in Excel file. So let's first look at the kmeans. Because wkmeans is called weighted kmeans, their AFW kmeans is also a way of wkmeans. So I put it here in one folder, and also kmeans input is put over here. Finally, we can compare the kmeans in this kmeans comparison file. So let's first look at the kmeans in the Spider or Python. So kmeans has a few functions that defined over here. The first one is kmeans grid search. Once we input the model and the raw data that we want to analyze, and also the parameter for the model. If you first we can parameter grade these parameters and then run in the loop to represent all of the possible models and save it, return as output models. So this function is to give given a model, raw data and the parameters, run all of the models and save in over here. So this output or return has many models. It is a list. The next function is called getMarks, is trying to give all type of clustering scores. For example, if I want to know the homogeneity score or adjusted random score. So this is the most important score that we want to validate a group way or cluster analysis. And when this adjusted random score is higher, that means our predicted result matches much better to the real index. So we can have more comparison of all of these parameter scores. The next one is to plot all of these parameter scores showing like this. So the next function is called read parameter. Once the parameter file in Excel is given, we can read all of the values here. And the next function is to plot learning curve in terms of the training size for X and adjusted random score for Y. For example, it's over here. We have training score and cross-validation score. When the training size gets larger and larger, these two converge to the same value, more or less. And the Y represents the adjusted random score. That's for this validation. And at last, we use the main function to realize all of the functions in one function. For example, first we read the original file that we want to analyze, the test4 Excel file, and drop the true value. Only keep the main data that we want to analyze. Let's look at this Excel file again. So true value, this means the group index. It's a real group index we can compare after we get the predictions. For example, this first object we predict is group 1, and we can compare with the group. Now is called group 3, so maybe it's a failure of prediction. Okay, so first we drop this line. Just take all of the useful data from here to the bottom. And the kmeans, we can use kmeans from the library because kmeans we have already imported from the sklearn cluster, and it's an open library that we can use very conveniently. And then we can read the parameter file from outside. Because it is the read parameter function is called over here, so it is targeted on the parameter Excel file automatically. And the next one is to use kmeans search function to search to create a grid for the models. For example, here. So finally we can get all of the models. And the next one, we can plot all types of scores in different models. First, we run all of the models. See this output. I runs all of the range of the length, and for example, output 0 because Python starts from 0, and we can read the first model using different parameters. And then when I equals 1 or 2 or 3, we can run different models. For here, we only have 5 models, output of 6. 0, 1, 2, 3, 4, 5. So we have 6 outputs or 6 models that we can run and show the marks and then print the best parameters using the best parameter search, grid search, CV function, and then plot the learning curve. And the next one, we can save the best model as test pickle file. And next, we can save the parameters in the CSV, like Excel file. Okay, last one is we can plot the learning curve. So this plot is trying to plot all of the scores, all of the running scores from homogeneity score to the last score. And the most important score is adjusted random score. We need to know. So this is kmeans all of the functions we can get it. So let's run again to see what happens. First, it gives all of the models from output 0 to 5, 6 models, and all of the scores showing over here. The models has different parameters. The first model is called, we have 3 clusters. Second one, we have 4 clusters. Third one, we have 5. So they iterate all of the possible models or possible parameters that we plug in through the parameter Excel file. And also random cluster 3, random cluster 4, random cluster 5. So at last we get the putting 5 folds, we get the final results like this. It shows the best parameters is initialization with we can use kmeans++, and the number of clusters we can use 4. That is the best way we can give the highest mark. And it takes 1 minute roughly to finish all of this. And okay, that's kmeans explanation of the coding. Next one is a class, kmeans class. Kmeans class has all the similar or the same functions. Kmeans grid search, get marks plotted, read parameter, plot learning curve. But here we created a class called the kmeans that we can use or use in the notebook or from outside. For example, here in the test class Jupyter notebook file, after we import all of the necessary libraries, we can just first read the original file, Excel file, and drop the index, true value index. Then we, because the kmeans equals kmeans, we already import the kmeans class. So this class is embedded over here. After using all of the functions, we can get the output and show the marks, all of the scores here, that we can use the functions directly from this file. So this file has many functions: k-mean, grid search, get marks, for example, plot learning curve, and read parameters. For example, get marks, we use this function in this notebook. It's coming from the kmeans class, and it shows all the results over here. Okay, that's about the kmeans class. Kmeans cloud that we can use from outside terminal. They all also have similar functions. For example, kmeans grid search, get marks, until the very end. But here, the difference is we use a system input. First, we can input 2 files, and then it will create 2 outputs. And let's see what it happens for this kmeans cloud. For example, I open the Anaconda prompt, the terminal. From here, I want to run the kmeans cloud. And here we have to put /parameter excel space test for excel file and there also one space between, so that we can put the 2 Excel files over here to see the result. It will take few seconds or 1 minute to see the result. By the way, don't want to waste the time. K-means predict cloud. It's same a cloud file that we can use to predict. How to predict? Once we create the output model and output result, as we see, output model is saved over here. We can save the best model in this test PKL, and then after saving, we can use the input model directly. And so, and the output results is also saved over here. That's for saving the parameters. And then here, over here, we can use directly to predict the new data. Okay, this has already been run. It gives the similar outputs, different models, 1, 2, 3, 4, 5, 6, and also different scores showing the from homogeneity score to the last score. The most important score is adjusted randomness score, and also shows the best parameters are this guy. And then next, we can run the predict cloud file. Predict cloud file, we have to only run one test Excel file because the parameters are saved, or the models are saved automatically. We can use directly from the input model. It's over here. So kmeans equals this load input model plus test PKL. So that's only one file that we can use. See what it gives to us. Okay, I think it's complete. So the first reading data file, and it shows the data file name test4 xlsx, and prediction done is after it's done, it will create a output result in the results CSV, showing the group result or prediction. It's over here, results CSV. For example, the first object, it predicts 2. That's cluster 2. And this one, it predicts cluster 1. So it gives different predictions corresponding to different objects. So that's a final result of this prediction. Hello everyone, today I would like to introduce more about the kmeans way to cluster. So how do we use wkmeans? Wkmeans, W is the weight. We can first initialize variable weights to attribute different weights to different parameters. For example, in our raw data, we have different parameters: silicon content, titanium, aluminum, ions, or whatever, calcium, or oxygen. For example, I would like to give more weight to this guy because this has huge variations than the oxygen. Oxygen, I would like to assume the weight equals 0.1, while I would like to give this guy or the aluminum for higher, for example 0.2 or 3, so that means these numbers are more important than these numbers for oxygen. So that's a basic conception of weighted kmeans group or clustering. So first one, I would like to introduce, there will be 3 Python files. The first one is wkmeans.py, second one is wkmeans class, third is cloud, and the same as kmeans, so each Python file has different functions. First, in the wkmeans.py, this file, so the first one is for variable weights initialization. For example, if we have higher standard value, deviation of one parameter, and the smaller mean of that one, that means this number, this parameter varies hugely, may be more important. That's why we want to attribute more weight to this parameter. So the next one is for random control centroid initialization. Of course, we need to give random points as a starting point to initialize the centroids. And next, to check if all the parameters fit the requirement. For example, the weight size is not equal to the data shape 1. That means, for example, we have 9 parameters: silicon, oxygen, iron, 9. If the weight size, because I want to give 9 different weight number or values, if this size not equal to this shape, I will raise value error. The next one is to give a sum of list of values square. It's a normal mathematical summation of square numbers. Get marks, this function we use frequently in the kmeans before, so it's trying to give all the type of clustering scores. The most important score is adjusted random score. It gives the final results to show if our prediction fits true index or true group number. The next one is random centroid initialization in a kmeans way. It's is much better than that random centroid initialization, because this way gives a randomization for the centroids in a more sophisticated and reasonable way, so that they will be far away from each other, so that they will not be very close. It will avoid some errors in the future iterations. So finally, we realize all the functions in main function. First, read the data files from outside in the folder. For example, our original raw data, test for Excel, that's what we want to analyze. And we drop the true value. That means group index or cluster index. Then analyze the raw data. Next, we can read the initial features from this guy. So the feature I gave to this Excel file, the first number corresponds to the number of iterations. So for example, I want to iterate 10 times, and also I gave 4 different clusters. That means the clustering numbers. Then we can initialize the centroid. Next one, this line is for the distance 0 initialization, because we need this distance for future use. The next one, calculate the weighted distances from centroids to all the data points. After we calculate the distance, weighted distance, because the weight times the distance, and then we can choose the least distant centroids to be the new cluster center for this data point, and also save the index over here. So after all of the iterations done, it's printed wkmeans finish. Next one, we're gonna plot the centroid distance changes before and after iteration. For example, this plot shows centroid distance changes. The first one is huge. After one iteration, it drops close to 0 and also goes to 0 gradually, or floating or dumping up and down. So that's for the plotting shows. Next one is to show the scores of weighted clustering by comparing the true index Y label, that is the true index, and the predict label is IDX, the index I gave here, by choosing the minimum distant centroid index. So get marks and compare these two guys. This is a true, this is predicted, and also save the predict results. For example, this is predicted, and also combine with the original data to give the final results saved in some Excel file. As you can see, the print showing gives a random score is around 0.8. It's not that bad and not that good. So let's look at the final results saved from this file. This is a true value or true cluster index, and this is a predicted index. It doesn't matter if 0 does not match 3, because computer doesn't know which group is which group, as long as it gives a different group. As long as different group can be different, that would be enough. For example, we can just change all the 0 to 3. As you can see, 3 corresponds to 0, and 2 corresponds to, this is a wrong prediction, but doesn't matter. For example, 0 corresponds to 3. It is consistent. So it doesn't matter for the prediction. We can change their values as we want, as long as they give the correct predictions for each group. So that's the final result saved over here. And the next one file I want to explain is a class. Class means we can build a class and then use all of the functions from outside. For example, in the Jupyter Notebook, you can show obviously online and from wkmeans class import everything, and this class is imported represented by this guy. For example, this plus plus function is wkmeans class. And also the calculate, this function is from the wkmeans class. So the wkmeans class dot means we have imported this class. And so similar iterations or codes, we can show all the initial centroids, that's the initialization, and group iteration for 1, 2, 3, and each group has how many numbers of their group members, and then the centroid distance change after each iteration, and at last the score results. So this one matters. Not every time they will have the same random score. So every time is random. And the next one is wkmeans cloud. So this is similar to wkmeans, but differently. We have introduced the output. That means we can write from the terminal and input all of the files, for example, the feature file path or data file path, and also save the output results. And as what we did in the kmeans. If I type in the terminal data file path, and it can be read automatically as this name and will be used later. Finally, it will be saved. The output result will be saved over here for the predicted results. It's the same as this process, but this file is for realizing the functions outside, for example, from the terminals. So that's all I want to explain for the wkmeans. So the next time I will explain the rest, kmeans input weight and AF wkmeans. So that's it. Hello everyone, today I would like to introduce a new way of clustering. So it's called AFWKmeans. It's in the WKmeans folder. If we choose this folder, there will be AFWKmeans py, class, and cloud, the three main files. And the main Excel file is test4. That is the data we want to analyze. Suppose 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 parameters that we can group them, and they have different contents in percentage. For example, they have 44% of oxygen. That is the main data we want to analyze. And what is the AFWKmeans meaning? If we look at this paper, AF means adaptive feature, W is weighted, so AFW is short for adaptive feature weighted means. And the main way we are utilizing here is it's around here. So there will be a DN and the DW, and CJ equals DW over DN. That is a contribution. So it's based on this way, and using this way we can attribute the weights in a more sufficient way. So the detail is in this paper. So let's explain from the beginning of this afwkmeans.py file, the Python code. So first, there will be a check if all the parameters fit the requirement function. It's similar to what we had before. The next one is sum of list of values squared, same as before. And next one, to give all the type of clustering scores. So this function is kind of changed because the input only has three parts. One is data, the rough data we want to analyze. The next one is true labels. Suppose the first one label is 3. It belongs to group 3, and this one it belongs to group 2. So that is the true labels, and the next one is a predicted label. That's what we predict in this way, in AFWK way, and then compare the true with the predicted to give all of the scores. So the most important score is adjusted random score. So the full score equals 1. If we have 0.79, that means it's more or less okay. And next one, it's called random centroid initialization in a kmeans++ way. That is using the kmeans++ from the current library in the Python, and to give the centroid initialization in a more sufficient way. Then we have our main function to compile all of the functions together. First one, to read the data file from outside in the folder. So for example, the first one we want to read is the original data file, test4 Excel. The next one is to read initial features from the feature Excel file. So what is a feature Excel file? It's same as before. We have two columns. One is the number of iterations, so it's set 10. We want to run 10 times, and number of clusters that we want to group them. And here we will have 4 groups in our prediction. So after reading all the test4 and the feature files, and we can initialize the centroids using ++ way. It's a sufficient way to initialize the centroids. Next one, initialize the distance starting from 0, because we can attribute new values to the dist, and then predicts initial centroids, like here. The printed initial centroids, that is the initial centroid we choose from the ++ way. Next one, constant weight initialization. First, we give all of the 9 parameters an equal value. That means 1 divided by the data shape 9 means 9, 1/9. And then we can update the W in a more sufficient way called AFWK way. And then calculate the weighted distances from centroids to all the data points in this iteration. Next one, choose the least distant centroid to be the new cluster center, and also take the index of that one. For example, 0, 1, 2, 3. That is the index we want to have. After we get the index numbers, and we will have the number of cluster members after each iteration and find the new centroids. So that is a new centroids update way to do that part. And the next one, adaptive feature weighted redistribution. So that is AFW with the key points of this code. So everything is different from here. First, we initialize a 0 and then use a sophisticated way to find the DDM over DDN equals CCL. That is similar to what we read here. CG equals DW over DN. After we find the contribution CG, we can attribute different values to the weights. As you can see here, the weight is updated using CCN over the sum of C. That is a new weight of each parameter. Next one, cluster quantities after each iteration is going to be shown. That means here, print group result iteration, this group result iteration, 1, 2, 3, 4, 7. So we run 7 times because I said if the centroid change less than the tolerance value, it's over here, 1e minus 7, and then it will break the loop. I will print AFWK means finish. So the value of here represents the number of the group members in each group. That is the group value stored here. Stored here. So after that, it's finished, done, and then plot the centroid distance changes before and after each iteration. It's showing here. As we can see, the first time the centroid distance change is huge and then slowly drop to close to 0, and it is stabilized after a few iterations. And next one, the last one, to show the scores of weighted clustering by comparing true index, that is y label, true index with the predict index. Y label with IDX show the marks, and it gives all of the scores. See, this one is important. Then the very last one, to save the calculated weights and predict the results, because we have calculated a new weight and new weights corresponding to different parameters and saved as AFWK means weight CSV, and also in a format shape in the time. As we can see over here, AFWK means weight as the time when it is recorded. And then also we save the predicted results because we predict the IDX, that's the index of the group, and then concatenate the original data with the new predict one and saved as results.csv in a time format shape. It's saved over here, as we can see, and it will show us the predictions correspond to each element, and this is a true index labels, and this is a predict labels. So as we see, they match each other, and here it's a little different. These two matches, and these two doesn't, and this one matches, so they give different predictions, and save over here. So let's all the codes in the AFWK_means.py. In the class, that means we have created a class, and in which we can use all of the functions inside of the class. For example, check parameters, give all the type of cluster scores, that means get marks, and also plus initialization, initial central initialization, so that we can use in the Jupyter notebook. For example, from here, the class we import everything and represent this guy, So the new plus plus functions is introduced from this class, and also some other functions. I think I can't find it now. So that's the way we use in the Jupyter Notebook. We can use the functions in that class directly and show the results. So the alt codes are copied from the original code, and it's to show the we can realize the codes outside in the Jupyter Notebook. The next one is afwkmeans cloud.py. This file is to run the code from outside. For example, in the unaccounted prompt, we first cd open that folder and run the file Python afwkmeans cloud.py. This is the file over here. And the first one, we need to give the feature Excel file and the data Excel file, because all the things are similar, except that we change a little bit here. We read the feature file path first, and then the data file path second from the system information. And the data file path is read as original data. The feature file path. Data file path is read from as here. Feature file path is read as feature, and then they can be utilized in all of the runs and also functions, new variables to realize all the results that we want to show them. And so if we can see first, Python, type the file name space dot slash feature Excel file space dot slash test for Excel space dot slash space dot slash. Then we can run all of the code from the unaccounted prompt and show the results. So that is a way how we use this afwkmeans cloud.py. Okay, so that's it. Hello everyone, today I would like to introduce a new way of clustering. It's called kmeans input weight, still based on kmeans, but here instead we use the input weight from outside. That is a constant weight. That we can have a look at this folder, kmeans input weight, and the weight from this Excel file. I want to give the values the same values to every parameter, silicon to oxygen, so that they are equivalent. And everything is the same. We use the same parameter checking functions, same sum of list, same of get marks, same plus kmeans initialization, the centroid initialization method. And also we read the file first and read the features, then get the distance 0 initialization, and calculate the weighted distance from centroids to all the data points, and choose the least distant centroid to be the new cluster center. So we can know the number of cluster of members after each iteration and find the new centroids. And the same thing happened. So at last we save the predict results and also get marks. So the difference is here, the feature weight, it's over here. Yeah, the weight equals reading cell weight. That's input from the weight we are reading, so that we will use that value from that weight Excel file to give all of the values, so that the distance over here, weight times the distance, we can find the distances from all the data points. So that's k-means input weight. The next one is k-means input weight class. It's the same as the method before. We set up a class so that we can use in the Jupyter notebook. So for example, from k-means input weight class, import everything, and also some necessary libraries. And then we can just type everything in the main function to have a understanding of what it runs. And then it gives a normal result showing the group number of group members after each iteration, and also result of the centroid distance change after each iteration. And finally, we got the adjusted random score around 0.71. It's not good enough, but not that bad. That is from the k-means input weight. And the cloud file, k-means input weight cloud, that means we can type from the unaccounted prompt the commander, so that we can control from outside to it. They are all the same as the k-means input weight. Difference is we use a system input and also save the output at last. That is save as a CSV file, naming output results and plus a time in the format is over here. Time result CSV, and it will give us the result, the predictions. So for example, the first four, the prediction is they give the same group index. It's not same as the true value of there, but we can change the the values of the group result. It doesn't matter. So these two same. This one roughly okay. So that is a final Excel file we output from this k-means input weight cloud or k-means input weight. And the last one I want to put more emphasis today is k-means comparison. Is from the k-means double k-means folder, k-means comparison. That is all the codes together to compare three different ways. The first way is double k-means, the second way is k-means, and the third way is AF double k-means, so that we compare all the three ways to see if their scores is better or not in this code. For example, starting from this line, we can see iteration 1 from 1 to 10, and after it finished, it gives us the results W k-means, adjusted random score, k-means random score, and AFW k-means adjusted random score, and also shows the adjusted random score. That is a result. It is to see, we can see if they are satisfying. And by looking at this one, the yellow one is AFW k-means. It's I think it's the best compared with the other two. The blue one is W k-means and the red one is k-means. In AFW k-means, we can see it's more stable than the other two. but sometimes kmeans may have higher rankings compared with the AFW kmeans. And also at the last, average adjusted random score is given, average of these three, and also the standard deviation, average of the W kmeans, because we have more many time trials, and also the standard deviation. For it applies for WK-means, K-means, and the AFWK-means, so that we can compare average adjusted random score for WK-means 0.71, K-means 0.72, AFWK-means is 0.76. This is the highest. And standard deviation also, AFWK-means has the least standard deviation, 0.03. It's less than 0.05. So we can see sometimes AFWK-means may give us a better solution for predicting the cluster numbers or cluster index. And everything is similar from the starting from the beginning. We import every library and define the functions. See, what is this? Okay. And define name std. Oh, maybe I deleted. I will just add numpy.std and numpy.min over here. np, because I import numpy as np. Maybe I deleted that library. I can just change over here. So now it's fine. Save it. So everything is similar from in the beginning. We use the same functions, variable weights initialization, using the standard deviation over their mean to give the weight, to attribute the weight to different parameters. And then sum of list of values square and clustering scores by comparing all the scores. And also the random centralized initialization kmeans++w, same as before. In the main function, I first put the read data file language first to read out from outside in the folder. First, the text 4, that's original rough data. Next one, we initialize the distance. First set it as 0, and then we can set initialize the adjust the random score at every iteration step for 3 different methods. At first I set y equals 310 because iterations equals 10, and this is a matrix of 3 by 10 matrix. Every element is 0. 3 represents 3 ways, and 10 represents 10 iterations. The first one is wkmeans method, and everything is similar as before. Finally, we get first print wkmeans finish, and then save the adjusted random score of wkmeans in 0y, because 0 represents the first way. It says wkmeans. Y means because y equals iterations from 0 to 9, there will be 10 times iteration. So they are all saved in this matrix. And the middle one is kmeans method. Similar, we say in y1y. Y iterates from 0 to 9 10 times. And the last one is AFW kmeans method. it's the same as before. We explained in the AFW kmeans how this method works. And finally, we save in y to y, and also small y runs from 0 to 9. Save it in this matrix. Finally, we compare the scores of adjusted random score in 3 different ways, so that 0, 1, 2, 3 different ways. As you can see over here, they represent different methods. And also score get the mean and also the standard deviation showing at last, so that we can see, compare which is better or not in two different parameters. The first one is average, the second one is standard deviation. That's a k-means comparison in this. So I think that's all the things I want to say. And also we save the figure in the training results comparison over here. So we can look at it, the result. So let me make a conclusion of everything. K-means, we have one method to cluster different data. Next one is wkmeans folder. It has wkmeans, the so-called wkmeans, and AFWkmeans, and k-means input weight. And finally, we compare all of the three ways: k-means, wkmeans, AFWkmeans. Because k-means input weight, we can change the weight from our view. We can use for the future use if we want to use different rankings from the first parameter to the last parameter, giving different weight values. We can change accordingly. So k-means comparison only compare three ways: k-means, wk-means, and AFWk-means. Okay, that's it. Thank you very much.